Today we're going to talk about what are called recursive rules for sequences, which is a different way of writing rules. So we learned in our very first lesson a couple of strategies that we could write a rule for a sequence of numbers. And then we learned some specific formulas that would allow us to write rules for our arithmetic or geometric sequences. What we're going to look at today are called recursive rules, as opposed to what we've learned so far are called explicit rules. And the difference is an explicit rule, you can plug in any number you want for n and find out whatever term that is. So if I wanted to know what the 123rd term is, I can plug in 123 for n and I can get it. For recursive rule, we're basing our formulas upon previous terms. So we're going to have some new notation that comes in these problems. So an explicit rule gives it in terms of its position in the sequence n, as opposed to a recursive rule gives the starting term. So we always need where does this thing begin, and then it tells how the next term is related to previous terms. The notation is a sub n minus 1 means one term ago, so like the previous term. Or a sub n minus 2 would be 2 ago, okay? That we're going kind of back 2 places in line. So we can base our rule upon the numbers that have already happened. Sometimes it's easier to write the rule this way. The downside is if I wanted to know what the 123rd term is, I need to know the 122nd and the 121st and the 120th, and I would have to work my way all the way there. So it's not as convenient in terms of coming up with numbers that are far down the line, but it's often easier to actually write the rule in this format. But we need that kind of new notation there that when we have a sub n, it's the now term. N minus 1 is 1 ago, n minus 2 is 2 ago, and et cetera down the line. So here it says, write the first 5 terms of the sequence, and a recursive rule always has 2 parts to it. It has where we start and what we do after that. Okay, we always need 2 parts to it. Where do we start, and what do we do after that? So we have our a sub 0 term, so that means our next term would be our a sub 1 term. And our rule says that for any following term, we're going to do n times a sub n minus 1. And we said a sub n minus 1 means 1 ago. Or another way of saying that is the previous answer. So what we're going to do here then is n, which is 1, because that's what the little bottom number is, times the answer from the last step. The answer from the last step is the starting term. That's our given. So we're going to do 1 times 1, which is 1. Then it said find the first 5, so we're going to keep on going here. Now our rule is a sub n, it says, is equal to n. So now that little bottom number is 2, so n is 2. And then a sub n minus 1 means last answer. So our last answer was 1. Multiply that and make it 2. A sub 3. Our rule is n, which is that bottom number, so it's 3, times a sub n minus 1, which means last answer. So that's 2, which gives 6. A sub 4. N is 4 times a sub n minus 1 is last answer. Last answer is 6. So we get 24. And let's come up with the first 5. So a sub 5 is n is 5 times last answer, and that gives 120. This sequence of numbers actually has a special name. It is called, there are factorial numbers. In math, we have a notation for factorial, which is an exclamation point, so we see real 3. But it actually, we read it as like 3 factorial. And what it means is multiply starting at that number and every number on down to 1. So 3 factorial means 3 times 2 times 1, which is 6. And that's what we got there for a sub 3. Or 5 factorial would be 5 times 4 times 3 times 2 times 1, which is 120, and that's what we actually got for a sub 5. So this just kind of has a special name to it. You don't really need to know that name. These become pretty important in probability, that we need factorials a lot in evaluating different probability ideas. But what we're concerned about here is not so much that these are called the factorials, but how we work with these recursive rules. We're given a starting place, and then we're given what to do after that starting place. So let's look at another example. Here we're given actually 2 starting terms and a rule that tells us what to do after that. You always must be given at least the first value of the sequence. Sometimes you're given more than that. And then we need what do we do after this. So we're already given a sub 1 and a sub 2, so the first thing we would need to find is a sub 3. In our rule, we're told to take a sub n minus 2, which means 2 answers ago, and add it to a sub n minus 1, which means 1 answer ago. So 2 answers ago would be a sub 1, which is 1, plus 1 answer ago would be a sub 2, which is 1. So we get 2. A sub 4. We're going to take 2 answers ago, which if I'm at a sub 4 would be a sub 2, so that's 1, plus 1 answer ago was 2, and I get 3. A sub 5 takes 2 answers ago, which was 2, and adds it to 1 answer ago. 3. That gives 5. This is like the first 5 terms. I guess we're at a sub 5, but I'm going to say let's actually find 5 of them since we were given the first 2. So a sub 6 is going to take 2 answers ago, 3, and add it to 1 answer ago, 5, and that gives 8. And a sub 7 takes 2 answers ago, 5, adds it to 1 answer ago, 8, and that gives 13. This sequence of numbers also has a special name. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, etc. They're called the Fibonacci numbers. So if you had geometry with me last year, you might remember hearing that. We learned about the Fibonacci numbers. We learned about something called the golden ratios. In geometry, they're actually learning about this right now. And this sequence of numbers has a special property that as we progress on through, if we divide the numbers, the later divided by the earlier, so like 55 divided by 34, or 89 divided by 55, or et cetera, they start approaching this number, 1.618, blah, blah, blah. And this number shows up in a lot of places in human anatomy and in art and in architecture. It becomes really important to just kind of create pleasing environments and proportions. Also, these numbers are really cool because they show up in nature, like in how many petals are in flowers, and how in a sunflower the seeds spiral, and how many spirals there are in that seed in the middle of the sunflower are actually always Fibonacci numbers. So this is kind of a cool sequence that definitely points to a creator, that these numbers show up in so many kind of unusual places. So here we've got one given term and a rule for what to do after that given term. So we're going to find a sub 2. Our rule says take a sub n minus 1, which means 1 ago, square it, and add 1. So 1 ago is the only answer we have so far, which is 1. We're going to do 1 squared plus 1, which is 2. And for our next one, we're going to take 1 answer ago, which is 2, square it, and add 1 to it. And that gives 5. A sub 4 is going to take 1 answer ago, square it, and add 1 to it. a sub 5 takes one answer ago, square it, and add 1 to it, and that gives 677. Questions? Alright, I want you to try this one then. In this one, we're given 2 starting values, and then we're given a rule with what to do after that. It says find the first, or write the first 5. I guess we're already given 2. I want you to actually find 5. So you're going to go all the way to a sub 7 here, so that you find 5 answers to this sequence. But go ahead and use those 2 starting terms and use the rule to find the next 5 terms of the sequence. Alright, so in our rule we have the notation for 2 ago, and then we're going to subtract from that, and we have our notation for 1 ago. Sometimes it's easiest to see this and perform these recursive rules if you don't worry about the notation like a sub 1, a sub 2, a sub 3, all that kind of stuff, but you just make a list. So if we just started our list with those first 2 numbers, okay, that we're given, then what we want to do is take 2 ago. So for this problem, sorry, for this next one, that would be this 2 minus 1 ago would be the last one, and that's going to give us 0. Okay, and then now again, I want to take 2 spots back in line would be 2 minus 1 spot back in line would be 0. And that gives 2. 2 spots back in line is 0, minus 1 spot back in line is 2, and that gives negative 2. And you don't have to show your work. I'm just kind of showing, where I'm getting these numbers. But on your homework, if you just made a list of numbers, 2, 2, 0, 2, negative 2, I told you to find 5, so we're in the 7th one. So then I'm going to take 2 ago, which is this positive 2, minus the one right before it, negative 2. So 2 minus negative 2, I get 4. 2 ago, negative 2, minus 1 ago. So negative 2 minus 4 gives negative 6, etc. And that pattern would continue. Okay. We take 2 ago and minus the 1 ago. And sometimes it's easier to see if you don't worry so much about the notation of the a subs, whatever, but just kind of write them in a list. And remember that our n minus 2 means 2 ago, and n minus 1 means the last one in the list. Okay. Questions on creating the sequences from the rules? Our next kind of problems have a little bit of built-in review here. We're told it's arithmetic, and we're asked to write an explicit rule and a recursive rule. Explicit is what we've already done. Right? So explicit, we learned for arithmetic back in 11.2 that our rules follow the pattern of the formula a sub 1 times, plus n minus 1 times z. Okay, that formula is back in section 2. And again, you don't have to have it memorized. You'll have all those formulas for you on your test. But that's how we write an explicit rule. So an explicit rule should have an n in it and no a sub things in it. Because then I can plug in any number I want and find out what a term of the sequence is, even if it's way down the line. So for this one, we're going to have a sub n is a sub 1 is 4 plus n minus 1 times d is 3. You always need to clean up your formulas. So distribute and combine like terms. So then I could find any term down the line with that explicit rule. So an explicit rule has an n in it, so we can plug in whatever number we want for n. That's a review. That's what we learned back in 11.2. Recursive is now the new thing. For recursive rule, we need 2 things. We need at least one starting value. So our starting value here is a sub 1 is 4. That must be a part of your answer. We can't have a recursive rule without being told where to start. And then we need a rule that tells us what do we do from here on out. So a sub n, from here on out, an arithmetic sequence is doing what each time?
Added by the same thing.
Adding. An arithmetic rule, we're going to take the last answer and add something to it throughout. So how do we say last answer? A sub n minus 1. And we want to add to that what? What are we adding as we move through the sequence? D, which is 3. The common difference is what we add as we move throughout the sequence. So what this rule says is start at 4, and then after that, just keep adding 3 to your last answer, which is what an arithmetic sequence does. It starts at 4, and then we add 3, so we get 7, we add 3, so we get 10, add 3, so we get 13, etc. on out is what an arithmetic does. Is it takes the last answer, and it adds to it whatever that common difference is. Okay. Look at another one like this. So again, for explicit, we have the formula back from section 2. So a sub n is equal to a sub 1 is 15 plus n minus 1 times d is 5. So we're going to plug this back into that old formula and then clean it up algebraically. Distribute and combine like terms. Okay, so a little bit of built-in review before we really review tomorrow and take the test Thursday. Now for a recursive rule, you must give 2 pieces of information. You have to give where do we start this thing. We start it with 15. And what do we do after that? So from there on out, for an arithmetic, we take our last answer, which notation for last answer is a sub n minus 1. And arithmetic means we add our common difference, which in this problem is 5. So this tells us start at 15, and then from there on out, just keep adding 5. Okay. This is the way students usually want to write rules at the beginning. When we start that very first lesson and we look at a sequence, we say, okay, what's happening here? We're adding 5. Oh, so the rule must be n plus 5. Well, it's not n plus 5, but it's last answer plus 5. And our notation for last answer is that a sub n minus 1. So this is kind of how students feel like instinctively to do rules from the beginning. We just need that new piece of notation that it's not n plus 5, but it's last plus 5. So here we're looking at a geometric now. Again, it's asking for explicit and recursive. We did have a rule for geometric that was back in section 11.3. So again, doesn't have to be memorized. You can look it up back from section 11.3, and it will be on the test for you. But this was our explicit rule for a geometric. So then we're going to have 3 times 0.1 to the n minus 1. And remember, we can't do any algebra or arithmetic on this to simplify it because order of operations says we have to do powers first, and we can't do the power because there's a variable up there. So we're not allowed to like multiply that 3 and 0.1 and try to clean it up that way. It actually makes it wrong if we do that. So that's our explicit rule, and we can plug in any number we want, and we can find the term of the sequence. For a recursive rule, we need where we start. So we're starting at 1, and then we need what do we do after we start. So it's geometric this time, and what does a geometric sequence do? Multiplies by the same thing over and over and over. And what is it multiplying by? 0.1. So it's taking our last answer, and it's multiplying it by 0.1. Okay, so for this one, we would have like 3.3, 0.03, 0.003, etc., and creating our sequence of terms here that we start at 3 and then we keep on multiplying by 0.1 as we move through the steps of this. One more like this. Again, we have our formula for our explicit rule. We can plug in what we know. We know we start at 4, and we know our R is 0.2. So that's our explicit rule that allows us to find any term of the series or sequence. And then our recursive rule tells us where to start and what to do after that. So after 4, after the first number, we want to take the last answer and multiply it by 0.2. Okay, and then geometric, we're multiplying by the same thing as we move through the line of numbers. Questions on those? All right, for our last type of problem today, we're going to be given a list of numbers, and we need to now find the recursive rule for the sequence. So in these, what you're going to look for is some sort of a pattern that's either taking the last number and doing something to it, or maybe taking even the last 2 numbers and doing something to them. So think about the different types of arithmetic we can do. We can, add, subtract, multiply, divide. We could square things. But how could we take maybe the last 1 or 2 answers and do something to them to get the next number? Oh, and somebody thinks they see the rule here. Let me know what you think you're doing as you move through here.
You take the last number and times it with, the second number and then times it with the first one.
Okay, so we're going to take the 2 ago and multiply it by the last one. So if we start with 1 and 2, that would just have to be given. And then if we multiply those, we get 2. And then if we multiply 2 and 2, we get 4. 2 and 4 gives 8. 4 and 8 gives 32. And so we're taking the 2 ago and multiplying it by the 1 ago. All right? So to write out a rule for this one, what we're going to need is actually 3 pieces of information. We have to give 2 starting terms since it's based on 2 terms. Since we're saying 2 ago and 1 ago, we have to give 2 starting terms. Otherwise, we wouldn't have enough information to begin the sequence. Then we have to give, what do we do after those first 2 numbers? We take the one that's 2 places ago in line, and we multiply it by the one that's 1 place ago in line. Okay, so we need 2 starting places, and then we take 2 ago and multiply it by 1 ago, and that will create all the other numbers in the list. Questions? And these problems are a place that can be very frustrating for some students because once you see the pattern, it's not extremely difficult to write the rule once we know the notation for like 2 ago and 1 ago. But sometimes it's hard to actually see the pattern. And that's something that really just takes practice. I can't give you like a whole lot of tips and procedures on how to do that, but just kind of think about what can we do with numbers. Add, subtract, multiply, divide, square. What kind of things can we do to create the next numbers? So take a look at these numbers and see if you can figure out how we can create them from 1 or 2 previous terms. Thinking about kind of adding, subtracting, multiplying, dividing, or squaring are usually our methods. Let me know when you think you see it.
It looks like you're taking the first one and adding it to the second one and then multiplying the whole thing by 2.
You got it. So we're going to take our first 2 numbers, add them up, that gives 2, which doesn't work for the next number, but if I double that, I do get 4. And then if I take 1 and 4, that gives 5, which if I double gives 10. 4 and 10 gives 14. If I double, that's 28. And that's as far as I can confirm in my head, but I could grab a calculator and do 10 and 28 gives 38, and I assume if I double that I do get 76, but I could grab a calculator and confirm that. So we're taking the last two answers and adding them together, and then we're doubling that. Okay, so since it's based on two answers, we again need to give two starting numbers. If it's only based on the last number, then you only need to give one starting number. But here it's based on two numbers, so we need to give two numbers. Then after that, we said we're going to take 2 ago and add it to 1 ago, and then we're going to double that. Okay, so we're going to take the last two answers, add them together, and double it, and that'll give us every number for the rest of the line. Alright?
Can I go get my book?
Yep. Your assignment's from 11.5 tonight.